Okay, we've all seen these mind-blowing videos that AI can create just from a simple text prompt. But here's the dirty secret. Behind all that magic, there's a mountain of computation that makes it incredibly slow and really expensive. Well, today we're diving into a paper called SpargeAttention2 that might just be the solution, promising a massive speedup without losing any of that amazing quality.
And this right here is where it gets absolutely wild. On the left, you've got videos made with a standard top-of-the-line model using what's called full attention. On the right, videos from SpargeAttention2. I mean, look at them. The quality is pretty much identical. The polar bear is shredding on guitar, the teddy bear is still rocking the drums. So what's the difference? The videos on the right were made with 95% less of the most expensive part of the process. How on earth do you throw away 95% of the work and get the exact same result? Well, that is the brilliant trick we're about to unpack.
All right, so here's our game plan. First, we're going to pull back the curtain on AI video's expensive secret. Then, we'll look at why some of the first attempts to fix it just didn't work. After that, we'll get into the 2 key innovations that make this new method so powerful, check out the incredible results, and finally, talk about why this is such a big deal for all of us.
So let's get right to the heart of the problem. The magic that makes these AI models work has a name, and that name is also its biggest weakness: the attention mechanism.
You can think of the attention mechanism like a huge, chaotic cocktail party. To really get the context of a scene, every single pixel in the video has to have a conversation with every other single pixel. Now, this is fantastic for understanding complex relationships, like how a hand holding a pick should move across a guitar, but it is a complete computational nightmare. The second you make the video longer or increase the resolution, the number of these little pixel-to-pixel conversations just explodes exponentially. And that is the fundamental bottleneck making high-quality AI videos so darn slow.
Okay, so if that's the problem, the solution seems pretty obvious, right? Just don't have every pixel talk to every other pixel. Let's make it focus only on the most important conversations. This idea is called sparse attention, but, the first attempts at this had a pretty major flaw.
2 main methods popped up to try and solve this: Top-k and Top-p. With Top-k, the model only looks at a fixed number of the most important connections, let's say the top 5%. It's a really hard cutoff. Top-p is a little more flexible. It keeps adding the most important connections one by one until their combined importance hits a certain limit, say 60%. Now, on the surface, both of these sound like pretty good ideas, but as you're about to see, they can fail spectacularly.
And this slide really just lays out the whole problem perfectly. The image on the left shows what's called uniform attention. That's where importance is spread out pretty evenly across a lot of different pixels. So a bunch of conversations are all kind of moderately important. The image on the right shows skewed attention, where just a few connections are incredibly important and everything else barely matters at all.
So here's the crucial insight. In that uniform situation, Top-k completely fails. It just keeps its fixed 5% and ends up missing all the other moderately important details. But in the skewed situation, Top-p is the one that fails. It can hit its 60% importance goal with just 1 or 2 super important connections, these are called attention sinks, and then it just ignores everything else. It's like going to that cocktail party and getting stuck talking to one person the entire night. You miss the whole party.
And this brings us to the first major breakthrough of SpargeAttention2. Instead of trying to pick one of these flawed methods, what if you could just elegantly combine their strengths?
This solution is so simple, it's brilliant. Instead of choosing, the model runs both. It calculates the connections it would keep using Top-k, and it also calculates the connections it would keep using Top-p. Then it just merges them together, taking the union of both sets. This hybrid approach means it never misses the broad context in a uniform situation, and it never gets trapped by an attention sink in a skewed one. It is, quite literally, the best of both worlds.
Okay, so we figured out what information to keep. That's a huge step. But there's a second, much more subtle problem. How do you actually train this new, super efficient model without, accidentally making it worse in the process?
Here's the thing. These massive AI models are pre-trained on enormous, high-quality and often secret datasets. If you take your shiny new sparse model and try to train it on a different, probably smaller dataset, it can start to suffer from something called behavior drift. It basically forgets the subtle things that made it so good in the first place. The paper even showed that fine-tuning the original model on this new data also made it worse.
And this is where the second brilliant idea comes into play. This quote just captures it perfectly. You don't want your new student model to just copy a new, maybe lower quality photograph. You want it to learn the technique, the style, the very brushstrokes of the original master painter. This whole process is called velocity distillation. Here's how it works. The original full attention model acts as the teacher, and its knowledge is frozen in place. The new sparse model is the student. Now, during training, they're both given the same input, and the student's only job is to produce an output that is identical to the teacher's. It's not learning from the new data at all. It's learning to perfectly mimic the expert. This lets it inherit all the quality and nuance of the original model while using its new super-efficient structure. It's genius.
So we have a hybrid attention strategy and a really clever training method. The big question is, does it actually work? Well, let's look at the results.
First up, the sparsity. SpargeAttention2 successfully ignores 95% of all those pixel-to-pixel calculations. That's a mind-boggling amount of computation that just gets skipped. And what does skipping 95% of the work get you? Well, it translates directly into speed. The most expensive part of the model, the attention mechanism itself, runs a staggering 16.2 times faster.
But this table right here tells the whole story. Look at the other methods, VSA and SLA. Sure, they get to high sparsity, but look at their quality scores. They drop. Now look at SpargeAttention2. It hits that same 95% sparsity, but its quality score is 64.92, which is actually a tiny bit higher than the original full attention model. And the generation time? It plummets from over 3,000 seconds to just 650. It's faster, and the quality is just as good, if not better. And if you want to see what those numbers mean in the real world, here it is. The prompt was for a couple walking in the rain. SpargeAttention2 up in the top left nails it. But look at the other efficient methods. SLA and VSA somehow make the man walk backwards. VMOBA completely forgets the woman in the prompt existed. SpargeAttention2 is the only one that delivers that incredible efficiency while actually sticking to the prompt.
So, okay, a faster algorithm is really cool for researchers, but what does this actually mean for the rest of us? Let's zoom out and look at the big picture for a second.
This is so much bigger than just one cool algorithm. Techniques like this are literally democratizing AI. By slashing the cost and the time it takes to generate amazing video, they are lowering the barrier to entry for everyone. It means more artists, more filmmakers, more creators of all kinds can get their hands on these powerful tools without needing access to a supercomputer. This is what fuels the next wave of creativity.
And that leaves us with one final, really important question to think about. We just saw a 16-fold speed up in one key part of AI. As these kinds of improvements keep happening and compounding on each other, making AI exponentially faster and cheaper, what does that unlock for us? What creative task that seems like pure science fiction today will just be a normal thing we do on our laptops tomorrow?